Hello, and thank you for taking the time to watch this movie about sea flowers and power mushrooms. So, I have been talking about SCIAMMBA gardens for some time now, and I've even mentioned some oceanic systems. This pair of ideas is for these marine systems, or possibly in very deep lakes and inland seas, so think about places like the Caspian Sea or Lake Baikal, for example. Okay, so let's go over the sea flower first. Check out this picture of a solar power generation system made by a company called Solar Reserve. As you can see, it kind of looks like a big flower. Well, the initial idea for the system was to have a big network of these things, only in the water. The way that Solar Reserve system works is by having the different mirrors all reflect the sun's radiation back to a central tower that transfers the sun's thermal energy from the reflected rays back to a reservoir of liquid salt that can be used to store the heat from the sun. This liquid salt is then used to power things like steam turbines when power is needed. Well, my thought is that we would do this out in the ocean, only we would also use the generation of steam in order to desalinate seawater through distillation as well. So we would have our sea flower system set up in an area with very deep and still water. We would also have systems nearby to cancel the waves, which I can discuss later. And it would have the mirrors propped up on little floats. And there could also be an underwater frame that held them into position so that they would basically be a floating version of the solar reserve system that we saw on the land. And they would send the sun's energy back to a central tower, and it would be used to heat the salt. And all that is about the same that happens with the solar reserve systems on land. And in fact, our liquid salt would also be used to boil water for a turbine, as is done on the land sometimes too. But here's where our system would start to get a bit different, because in our systems, the water being boiled would be salt water, and we would be trying to separate out the fresh water from a saltwater brine. So let's try and imagine that we have our heating element here, and it has pipes with the heated liquid salt in them, and they are being made with a highly thermally conductive metal surface that heats the seawater to boiling. Okay, so the seawater is pumped from the heater, and some of it is boiled as it goes by. The portion that is not boiled off into steam is then pumped out as new seawater is pumped in, and the steam is used to generate power by driving a turbine. And then, after driving the turbine, the steam is sent back in a tube along the tube that initially fed the system seawater to the heating element. And the pipes are thermally conductive, so the steam gets cooled by the incoming seawater, and the incoming seawater gets heated by the steam, and as the steam cools, it condenses and gives us fresh water. Let's also do something kind of similar with the concentrated brine that was left over when we boiled the seawater off. Let's also run it in thermally conductive pipes along the pipe that takes the water into our system, cooling the brine and heating the incoming seawater. This time, though, we don't really get as useful of a byproduct, just cooled brine that we can either send back to the ocean or possibly use to set up flamingo habitats. Because the SCIAMMBA gardens might displace flamingos from their briny habitats, I have thought about the possibility of setting up these big floating brine shrimp habitats out in the middle of the ocean to make up for it. But back to the sea flower. So we have our big solar system that heats the salt, and then this salt is used to heat our seawater. The seawater being piped into the chamber with the heating element is heated by the hot brine and the steam that are exiting the heating chamber. And in the end, we get electrical energy from the steam and fresh water too. Okay, so how should we set up the tubes for this? How about a big long set of tubes in a horizontal line? Or what about if we spiral them together? Or maybe we should have something that looks even more spatially compact, like your small intestines or something. Or what about if we had the tubes head straight down? Why would we want to do this? Well, we are taking one amount of liquid fluid down and sending less liquid fluid back up, and the steam will rise by itself. In other words, we would be setting up something where we could generate power with turbines, like the Francis turbine systems set up in Hoover Dam or something. Only our system would also heat the seawater as it headed down. So the seawater would head down the central stem pipe, and it would build up heat and pressure as it did so. Once it ran through the turbine at the bottom, it would enter an environment with vastly lower pressure than in the central steam pipe, and most of the volume could flash vaporize at that point, leaving only a concentrated liquid brine that would pool on the bottom of the system. In fact, instead of having our steam pipe go alongside our central stem pipe, let's have it completely envelop it so that the central pipe is totally jacketed by the steam pipe. The liquid saltwater brine would then get pumped to the surface through the steam pipe as well alongside the central stem pipe. Now, raising this smaller amount of liquid back to the surface would cost us some energy, but it would be less than we got from running the far larger initial volume of seawater through the system. And again, most of the volume from the seawater would be changed to the form of heated steam, and that would rise up out of the system's base and get used to heat incoming seawater at the top, perhaps even after driving a second steam turbine underwater or at the surface. I'm thinking that the huge outer tube might be made of bricks formed from a compressed material that could be mixed at the surface and then lowered into the ocean in special presses that uses the ocean's pressure at great depths to form huge blocks. The picture you see here is from an article in Popular Science about a machine that makes bricks for construction projects today. It takes a mix made mostly of dirt but with some cement and water mixed in, and then puts it into a press that applies 55,000 pounds of pressure down on the bricks to press them into shape. The system for the much larger blocks that we would use would function in a similar way, only it would use the ocean's pressure, which is much more powerful per unit area than the hydraulic press depicted here at the depths that we're talking about, in order to press the ingredients together. The big blocks would then be cemented together for construction, but what would really hold them together once the system was up and running would be the ocean pressure. Once we finish assembling the system, we will pump the seawater out of the inside so that we can install the other parts, and this will cause the blocks to lock tightly against one another. My thinking is that a system like this would be relatively cheap to make very thick, which I am hoping would also make it very strong, and would additionally make it a good thermal insulator. We might even use several layers of blocks, maybe with different kinds in different layers. I'm imagining that we might also want to paint on some kind of treatment once the system is assembled, like an underwater paint that might keep the outer surface of bricks smooth and help it deal with the ocean water. So it's a really long, really thick structure, but my hope is that we can still make it relatively cheaply because the construction materials would be mostly dirt, and we would be using the ocean's pressure to press the bricks for us. By the way, if you think that this kind of a system might make sense, but are concerned about our ability to build something miles down in the ocean, consider that we might be able to use mine shafts as well. The Tautona mine in South Africa, for example, is listed as unused and 2.4 miles down here on Wikipedia. So if we wanted to, we might be able to make systems that were built into tunnels, dug into the Earth's surface as well, and that way we wouldn't have to deal with the constant problem of ocean pressure going forward. As I have thought about this problem, an interesting thought has occurred to me. Let me ask you this: how deep do you think that we should make our system? I seriously think that the answer might be as deep as possible. Let's imagine that you have X rate, volume over time, of seawater running through your system, and you have it set up to where it has a 100 meter drop. Well, that kind of a system might work well, but why not have a 200 meter system? Or why not have a system with a 10,000 meter drop? I mean, there's parts of the ocean that go that deep. Is there a point at which it doesn't make sense, or are we merely limited by our inability to construct systems much deeper than the ocean is? This is where the power mushroom idea comes in. Forget about seawater and trying to generate fresh water at all. Take a look at this chart. As you can see, water has a very high heat of vaporization. This means that we need to put in lots of power for our system to get our fluid to boil. So let's replace the seawater in our system with some other fluid, one that is more energetically cheap to boil into vapor, and one that doesn't leave us with a concentrated brine to deal with. And since our new system won't be taking in seawater and producing steam, let's close off the top. Could we then get rid of that part, the flower part, and just replace it with a big mushroom cap shaped heat exchanger? That's the question of the power mushroom. But what would drive this kind of a system if not energy captured from sunlight? Molecular kinetics is what I think. There is an incredible amount of energy all around us that goes almost completely untapped today. Take a look at this lady doing a demonstration of how to perform biceps curls. You could say that she is doing work, right? Because she is accelerating a mass over a distance. And we would all agree that this is the formal definition of work. But what if I was to tell you that there's an incredible amount of work being done on the metal in the weight that she was curling before she even picked it up? Take a look at this atomic model from an online class on moving molecules in a solid offered by the American Chemical Society on YouTube. In the first part of the video, the person demonstrates how a metal sphere, which can pass through a tightly fitted circle while room temperature, is unable to do so once heated, but then able to pass through once cooled down again. And this is explained by relying on molecular kinetic theory and arguing that the molecules are kinetically excited by the added heat, and that the expansion is a result of the more powerful motions on the molecular scale. Well, the molecules are vibrating back and forth, moving at incredible rates. I'm not sure exactly what kind of rates there are in steel, for example, because I don't know as much about inorganic chemistry or where to find that info, frankly. But in organic compounds, rates for molecular stretching or twisting motions, for example, are in the tens of trillions of cycles per second range. And so, if work is a measure of acceleration of masses over time, then there is a huge amount of work being done at the atomic scale at all times, because we are talking about the atomic nuclei in the molecules in question being moved back and forth, necessarily including accelerations and decelerations for this, and the atomic nuclei are where almost all of the mass in the atoms is located. So the atomic nuclei in the metal weights have mass, and they are being accelerated, and therefore there is work being done on them even before the woman picks up the weight to do her biceps curl demonstration video. Or think about the inside of this basketball. She can compress it over and over by dribbling it on the ground, and it will still keep bouncing back as long as the air in the ball doesn't leak out and it remains at room temperature. There is a lot of work being done just to keep a basketball bouncing for a whole basketball game. It's just that people don't realize it. There is also a huge amount of work being done keeping our atmosphere way above our heads. I mean, just take a look at this model of helium under pressure from Wikipedia, and remember that it is sped down around 2 trillion times. And the mass of the atmosphere around us is about 5.5 quadrillion tons. So imagine something weighing 5.5 quadrillion tons accelerating and decelerating around like these tiny dots, only 2 trillion times faster, blasting itself miles, hundreds of miles above the surface of the Earth. And you can get some idea of the truly huge amount of work that is being done at the atomic scale in order to keep the atmosphere up so high above our heads. And this is also what keeps the basketball inflated when it's dribbled. All these little air molecules transferring molecular kinetic energy to the inside cover of the ball. And this is the power that will be lifting our steam for us too. We will keep our fluid in the liquid phase on the way down the central stem, and then use molecular kinetics in the gas phase like this to lift it back up to the top. I even wonder if we might be able to build a space elevator with one of these systems. For those of you that are unaware, there's an orbit around our planet called geostationary orbit. The idea for a space elevator is basically to have a system out past geostationary orbit that has a tether connected to the Earth, and the tether would then allow people to ride it up into space. The problem is that there isn't a currently available material that could handle the stresses involved. Things like silks, artificial silks, Kevlar, those are the best materials that we could currently use, but none of them can reach the distance necessary. Some people think that carbon nanotubes could maybe be used in the future. What if we had our tether supported by big electrically driven rotors? Let's imagine that for every mile of tether, we have a big system of fans connected to the system that would provide lift, like a bunch of little helicopter blades to keep the tether up. The problem is that you run out of atmosphere. Eventually, the air is too thin to give us enough lift. But what if we had the gas trapped inside of a big tube, like was the case with the system that was under the ocean? What if we had a huge power mushroom that went all the way past geostationary orbit? Let's imagine that we have turbines on the inside of the system that get power from the current of gas, as well as keep the system up. In fact, we could have systems like these installed just after the dam-like turbine, even on the systems I was talking about in the oceans, operating as a steam turbine the way that I mentioned the system on the surface had. That way we can benefit from the energy released when the gas expands due to vaporization. And some of the ones lower down might be made of one rotor that wraps all the way around the system rather than two like I showed before, creating what looks more like a traditional steam turbine. In this picture, the one shown here, the fluid flows down the system as an extremely hot liquid through the thin center pipe. It is then fed through a turbine similar to that found on dams today. It is then flash vaporized through a nozzle, and much of the volume is converted to steam. The portion that remains liquid is allowed to drain into a pool at the bottom where it's boiled into steam by electric heaters. The vapor generated is then used to drive a big turbine fan that rotates around the center pipe, supported by a big ring that connects it to the outer wall. Here I've only shown one of these fans, a very big and open one with only 3 blades so that I can show and explain it. But real systems might have several rows of rotating blades set much more closely together, kind of like a giant version of what you might see if you look into a big turbofan of a jet airliner today. In fact, for really big systems, like on the bottom of the ocean, I think we might even have a few sections where the fluid exists as a supercritical fluid before finally being able to enter the gas phase higher up. You might be thinking to yourself, but wait, didn't we just extract the energy from that fluid flow with the system that functions like a dam's turbine? How can we also extract energy with this second system? Well, we did get energy from the dam-like system, but that was extracting a different kind of energy. The system that operates like a hydraulic dam only runs on the pressure difference between the liquid going in and the liquid going out. It has nothing to do with the expansion of the fluid due to temperature. Then, once the fluid has already exited the dam-like turbine system, we can allow it to enter a much lower pressure environment and get additional energy from the expansion we get from heating it up so much. So now we have two separate turbine systems running, one that takes advantage of the difference in pressure while the fluid stays in the liquid phase, and one system that takes advantage of the expansion of that liquid into a gas once it leaves the first turbine. And I do think that these systems could be combined into one system, of course. I just wanted to separate them out here initially to demonstrate that we are getting more power down here than from a simple steam turbine that we had running on the surface without getting an advantage from the drop in height. If you are having a hard time imagining how this whole thing is meant to hold itself up, then please consider for a second the case of these things the company making them calls air dancers. As you can see, these soft fabric sack people are held aloft in the air because of the current of air flowing through them. Well, the system that I'm thinking of would be similar, only reinforced enough so that we eliminate the different waving motions you see here, and with an additional system of internal rotors that resist the motion of the air current and provide additional lift for the structure. Well, would such a system work? Maybe not. The space-based power mushroom idea is pretty out there, but I do think that I'm onto something at least with the sea flower idea. The idea of having the ability to generate power and fresh water at sea is attractive, and I do think that at least some drop down could be useful, even if it's just like 100 meters. If you find this stuff about organizing the power of molecular kinetics interesting, by the way, please also check out the Space Flower Ship movie that I made for Emily Willow. It can be found at this address. In the Space Flower Ship movie, I think about how we might be able to set up a system that allows us to accelerate things in space without pushing off on any external surface or propellant. I've even tried to come up with a way of combining that system with something like the one that I'm describing in this video, only in a space-based system that orbits the sun. It has a huge parachute-like reflector that captures a large area full of the sun's radiation. But back to the power generating systems, if we do get an advantage, even from a system just dropping the water like 100 meters and having the steam rise back up for free, I do think that it's the organization of molecular kinetics that we can thank. Do you see what I mean? I have actually tried to get people at the local college actually interested in this idea, but I can't seem to get anybody excited. Most people just don't seem interested at all, which is something that I find frustrating. Or to concentrate more on the specific feature of the system I want to focus on here, let's completely leave out the steam turbine part for now in the complicated settings. Consider the following situation. Let's imagine that we have a factory in a city today that just needs to boil water to make steam. They have to iron shirts on an industrial level in the factory or something, and this is how they make their steam. So we're going to be boiling this water anyway, and in this case, we're going to be using electric water heaters to do this, and we're going to be using power from the grid. Now let's pretend that we have a part of the factory that goes down 100 meters. So our water comes into the factory from the tap, and we heat it with the electrical heaters, which spew out steam and allow the steam to rise back up 100 meters to the top in a steam stack. We could try and get some power from converting the water into steam with a turbine system like I was talking before, but let's just, for this simplified version, ignore that. All we're doing here is just making steam. Okay, so then let's pretend that we have a situation where the water is ready to be made into steam like before, but where we take the water and drop it down like 100 meters and put it through a small hydroelectric system before then having it boil into steam and head back up the steam stack to the height that we started at, 100 meters up. Would this system save energy if we didn't have to consider the construction costs compared to the system with no drop? In other words, sure, it might be more expensive to make this kind of a system, and especially when you consider the small height of the system, it might not save all that much power, and so it might be more expensive to build than it's worth. In other words, the economic advantage to such a system is not what I'm interested in, but whether or not simply you would gain an advantage only in terms of being able to convert liquid water to steam using less grid electrical energy per unit volume of water once the system was in place than without it because of the energy provided by the addition of the dam-like turbine. I like this more simplified example for a few reasons. One is that the small hydroelectric projects with 100 meters in hydraulic head height are very well understood things, as they exist all over the world. You can even go online to various places and see calculators set up to show you how the power output of a system can change with head height, as you can see here from Engineering Toolbox. And steam stacks are also very well understood. And unlike with hydroelectric installations, the height of the system isn't so important as is how well the steam stack is thermally insulated, though obviously longer systems are harder and more expensive to keep insulated well. Because with most steam stacks, all you need to do is make sure that the steam in them stays in the gas phase, and you can be sure that it rises out of the stack. So let's imagine that we have a system where we only heat our water at the base of the system, like the one I described. We need to make sure that the temperature of the steam heated in the system, headed up, stays above 100 degrees Celsius, and we need to make sure that there isn't too much pressure buildup. So if we imagine the energy required to send the steam up a 200 meter steam stack instead of a 100 meter one, the energy required won't be that different as long as the system is well insulated. We might have to invest a bit more in heating our water to keep it warm enough to reach the top, or even install some heaters on the way up to help us out a bit, but that isn't too energetically expensive. If we have bad insulation, of course, it will be a different story, and we're going to need to invest significantly more energy to raise the steam the extra 100 meters. But let's pretend for this example that we have a well-insulated steam stack that can handle it. I believe that this bottom system, the one with the drop and the hydroelectric generator, will save energy compared to the top system without it. The reason is this: we get a relatively large benefit from making the system longer while having to pay very little cost to do so. And this is why I've tried to show this example to other people, but I've yet to find anyone that is convinced. Why? I don't know. I've taken this setup and explained it to a local physics professor, for example. I explained to him that the hydraulic head height of the system like this and the amount of power that the hydroelectric system set up on it share a linear relationship, so that when you double one, you double the other. Then I had him try and consider the steam stack, where in the most extreme examples, you only need to heat up the water a little bit more to account for the extra chance to cool going up when you double the height. And in an ideal setup, one with near perfect insulation, you'd hardly need to heat up the water more at all. Do any good. Most people seem to think that my idea would somehow violate the law of the conservation of energy, but my response to this is that you shouldn't blame me. It's the atoms themselves that seem to be in violation of the law. They're constantly doing all of the work that, as I explained earlier, you can detect with things like IR spectroscopy. If you believe, as they tell you in organic chemistry class, that the atoms around us are stretching and twisting and bending and scissoring and rotating and all these other moves that the atoms are supposed to be making around their covalent bonds with other atoms in the matter surrounding us, then you believe that there is constantly work being done on the molecular scale. Almost all of the mass in solids around us is in the atomic nuclei of the atoms that make them up. So let's think about a couple of atoms in a solid that are undergoing the basic stretching motions you see here. The two atoms are moving away from each other, then they slow to a stop before accelerating in the other direction and then slowing again, and etc. Well, my argument is that this is no different than the work being done by someone moving the whole solid, like that lady with the weight that she was doing arm curls with earlier, where they accelerate and decelerate the thing, only this work is happening at the subatomic scale. So if you can buy that, then I think you can buy my argument that the other two phases of matter, by which I mean gas and liquid, of course, I'm not talking about plasma at any point here, are constantly having work done on them because they also exhibit locomotion. In other words, their molecules are actually totally moving around, changing their position, and don't just move around in the same general place as is in the case of solids or the lady doing arm curls, for example. So perhaps I am wrong, but I'm convinced that there's a large amount of work being done by all the atoms around us that exist above 0 degrees Kelvin, and that the devices that I'm thinking of are going to simply tap into this work that's already being done and not themselves generate any energy, as might supposedly violate some law of thermodynamics. And please, just think about it. It makes sense. Think about this simplified example with the factory boiling water. It makes sense that just dropping the water down 100 meters would actually generate a large amount of energy, because that amount of head height is actually fairly large compared to many real-world micro-hydroelectric projects today, and it makes sense that the steam generated will rise back up the 100 meters or so for free because there's many steam stacks that are taller than this operating in the world today. And it makes sense that the same sort of system would work even better for a 200 meter drop or a 1,000 meter drop, as long as the steam stack was well insulated, because you keep getting massive payoffs on the hydroelectric side of the equation every time that you increase the head height. While on the steam stack side of the equation, the steam just keeps rising for free, or nearly free if you need to install small heaters in the stack to keep the temperature up. because of the locomotive molecular work being done that I was talking about a bit ago, using the same work that is done by the air molecules in a basketball every time it bounces back up from the ground after being compressed into it by a player dribbling it, or the work that keeps other air molecules hundreds of miles above our heads, and the work exhibited by the helium molecules you see modeled here. Finally, please take a minute to think again about the example with the factory. It is made of 3 parts, all of which exist today and are all well understood. There's the water heater, these exist and they're understood. There's the hydroelectric system, these exist and everyone understands how they work. And finally, there's a steam sack. Again, this is a technology that is currently being used, and in fact they've been commonplace throughout the industrial era. Well, if you believe that these 3 pieces of technology will work separately, then why will they not work together as I've claimed? And why would you not save even more money if you increase the height or depth depending on one's perspective of the system? And if we could build such systems and they would save energy, then why? Why, if not for their ability to harness the kind of work being done by all the atoms around us on the molecular scale, would this be happening? I'm telling you, I think that I've come up with a way of harnessing the power that keeps the sky high above our heads. Of course, if we simply substitute a steam turbine in for the water heater, we've pretty much gotten back to the system that I started out describing in the ocean. Anyway, thank you very much for taking the time to watch this movie. My hope is that if I can get enough people to watch it, hopefully I can finally connect with someone that's interested in helping me make this. I hope you have a nice day.